Now that we've discussed the virtual light sources we use to illuminate a computer-generated scene, let's examine different approaches to simulating shadows. We'll see in another lecture that the brightness of a 3D surface can be determined by considering incoming light vectors, right? So if we had some 3D surface, we can figure out how that surface is being illuminated by just taking basically the light emitted from various virtual lights in the scene and just considering that as an incoming vector, right? And we'll use this information to determine the illumination on that surface. However, if we don't explicitly check if there's an object in the way, so let's just quickly redraw this actually. Let's redraw this as if there was an object in the way here. If we don't actually check if something is in the way, like in this scenario, rendering this point in shadow, we would have no way of knowing if, said surface point is in shadow or not. All right, so now, at least in the context of rasterization-based real-time rendering techniques, which is so far all we've discussed in this course, we're going to need to take some extra considerations for if light rays are being obstructed by some objects in the scene, and if whatever surface point we are observing on an object is in shadow or not. Now, ray tracing, which we'll discuss in another lecture, introduces yet another way of simulating shadows, but we're not going to get into that here. Let's start by discussing some shadowing techniques primarily used in the past, and not so much nowadays, but they're still interesting to look at to see just some alternatives to a more modern approach for real-time shadowing. So the first one we'll look at here is called projection shadows. And with projection shadows, we will actually be limited to projecting shadows onto a planar surface. And we'll see why this is in just a second. So with this method, the object casting the shadow, let's say it's this cube-like object here. Just draw that in. In order to get this projection shadow, what actually ends up happening is based on the position of some light source, we actually perform a transformation. We use a matrix and perform a transformation on the vertices of this object and project them, each of them, onto the plane. So, let's see here actually. This one would go roundabouts here. This would be somewhere here, roughly speaking. Just trying to estimate what the shadow would look like coming off of this point light source here. But roughly speaking, we would end up with some sort of projection like this. All right, and this surface area would be considered to be in shadow. And again, I just want to make it clear what's happening here. We are actually projecting vertices, each one with its set of three-dimensional coordinates into two-dimensional space, the two-dimensional space of this plane. And this is why projection shadows only work with planar surfaces. We can't do this onto a curved surface. So yeah, that's one, a fairly simple way of getting shadows. And, we can expand on this. We can start simulating soft shadows by introducing, not just a point light source or a directional light source that's infinitely far away in the scene, but we can actually start to introduce a light source with a surface area and basically simulating this projection from different points on the surface area of, what we could consider to be an area light. And we'll see this idea return a little bit later on when we talk about shadow maps. But yeah, just as a little precursor to that, we actually can kind of introduce the idea of soft shadowing, even with something as simple as projection shadows. Although, again, this method isn't commonly used anymore. All right, so there's projection shadows, fairly straightforward. Let's move on to a different historical method for doing shadowing. So as we just saw with projection shadows, we can only cast these onto planar surfaces, right? So what if we were dealing with an arbitrary surface, maybe some sort of curved surface like this? How could we approach casting shadows onto something like that? Well, in this case, we can start to use the idea of shadow volumes. So what do I mean by a shadow volume? Let's just quickly draw out an example of that just so we all understand the terminology here. Let's imagine a very simple scenario, actually, just a single triangle polygon. And let's imagine a light source positioned somewhere out here. And so what we could do is, get a projection of sorts of the object itself onto whatever arbitrary surface we're dealing with. This is going to look a lot like what we just saw with the projection shadows. However, we're not literally projecting these vertices of the object onto the surface itself, right? We can't do that. It's a curved surface. But what we can obtain actually is a volume. So let's now kind of ignore the top part of this sort of pyramid shape. You could think of this as a truncated pyramid, right? A pyramid with the top roughly cut off. Just imagine that connected there, and we could imagine this area underneath the object itself to be a volume. This area down here. All right, so this is the shadow volume. This is the area in which objects will be in shadow because their line of sight, if you will, to the light source is obstructed by some object. All right, now I'm going to need to redraw this in a simpler format to talk about the algorithm used to render certain surface points in shadow or not in shadow. So I'll just draw this from the top looking down. All right, let's get kind of some surface to render, and let's put in some object here. Let's just do a very simple object, something like this. And let's go ahead and render the scene from this point of view. I'm going to put my camera right over here, and you can kind of imagine we're rendering in this direction, right? So every pixel, as we're rasterizing every pixel here, we're just taking a look out into the scene and kind of rendering this information here. All right. And so let's redraw that shadow volume. Again, we've got a light source of some sort, and we're going to be getting, let's try and draw that a bit more accurately. Something like that, and something like that. I want this to be as accurate as possible. All right, so this would be the shadow volume. And so let's say we are rendering some pixel of the final image that ends up, according to the Z buffer of the camera, the closest surface point, unobstructed surface point to the camera would be this one right here, right? So this is, of course, the visible surface point, and we want to figure out whether or not that point is in shadow or not. So all we're going to do here is keep track of a simple integer counter. So we could just call this, let's get another color here, call this the shadow counter. And start it off at 0. And basically every time we intersect the boundary of a shadow volume, we increment that counter. Just add 1 to it. And so once we reach the surface point that we're rendering here, if that shadow counter is non-zero, then, well, we're going to know that that surface point is in shadow. Now, let's compare this to another scenario using the exact same algorithm to see how it works. The algorithm is going to work even for surface points not in shadow. So I'm actually just going to quickly redraw this, and resetting that shadow counter back to 0. Let's grab that blue color and set the shadow counter back to 0. We're going to be rendering from this camera angle. We're going to try and render something like this surface point right here. All right, that is the surface point visible to the camera. So let's follow the same algorithm here and see what we end up with. So do note that I've created 2 shadow volumes here being cast by these 2 objects. So one shadow volume and another shadow volume. So this example is getting a bit more complicated using 2 shadow volumes here, but let's see what happens. So we enter a shadow volume, therefore we increment the counter. But then, hey, look at that. We actually are able to leave a shadow volume as well. And so what we're going to find in this case is we actually decrement that counter, subtract 1, bring it back to 0. And this is going to allow us to, exit shadow volumes and render certain points not in shadow if they're not in a shadow volume. And we can go ahead and follow those rules again, incrementing when we enter the next shadow volume, decrementing when we exit back to 0. All right. And so in a different way from the last example that we just saw, since even though we passed through 2 entire shadow volumes, that has not affected the fact that this final surface point here, as we render this final surface point visible to the camera, the value here is 0, and since that value is 0, we can safely know that that visible surface point is not in shadow, right? So it's just a simple set of rules: increment a counter when we enter a shadow volume, decrement when we exit, and that will work for us for the shadow volume shadowing technique. Now, it is worth noting that this is just the general idea of how shadow volumes work. However, when this is implemented, it is optimized using something called the stencil buffer, which we're not going to get into here because, again, we're not focusing on shadow volumes in this lecture. But it is worth noting that this is handled, again, using something called the stencil buffer. And now we come to shadow mapping, which is the most versatile of real-time shadowing methods and is the technique used by modern game engines and other real-time rendering engines. So with this method, the entire scene is rendered not only from the camera's point of view, but also from the point of view of each light source. So that is probably going to sound a bit strange. Let's draw out an example here, just showing, the typical scenario. Let's try render this object, this blue cube, and again, we'll have just some sort of a backdrop here to cast a shadow onto, some sort of object at the back here. And of course, we know what the Z buffer is, right? We know that for every pixel of the final image here, we are storing the distance, right? The Z component of the surface point visible to the camera. We are storing that distance from camera to surface point. And of course, that will represent the closest surface point to the camera, the one that's actually visible to the camera and unobstructed by any other objects. And actually, just to make this example work a little bit better, I'm going to move the camera over so that we're able to both render this a surface point like right here, and a surface point on the backdrop as well. All right, so we get this. We've done Z buffers. We understand what that means. But with shadow mapping, we're going to need to basically generate a Z buffer for light sources as well. And this is where things get a little bit more interesting, right? So here's some light source, and we know how this works. Let's just figure out roughly the shape of the shadow that should be projected by that light source. And so basically, we're following the exact same process here in generating the light's Z buffer. We actually create a square image. You can think of it as a texture with just a bunch of pixel values. And they're going to be grayscale pixel values, just like in the Z buffer for the camera. And so that Z buffer is just going to contain, the distance from light source to various surface points, right? The closest unobstructed surface points in the scene, right? So these ones would end up, at a Z value, a fairly low Z value, fairly close to the light source, but these ones would end up being a lot larger as the Z value being stored is a lot farther away from the light source. I'll just get rid of those lines because we don't want the drawing to get too confusing here. All right, so now when the scene is rasterized, a camera Z buffer value, so for example, this point right here, is actually transformed into light space. So in the same way that we can transform coordinates, from object space to world space, and then world space to camera space, we can obtain a matrix to transform camera space coordinates into light space. We can figure out where this surface point is relative to the light source, and then we just compare the Z values. So in this case, the Z values are going to be identical because, the distance from the light source to the closest observable point is going to be the same value here that was stored for the camera, of course, transformed into light space. But these Z values will be identical, right? There is nothing obstructing this surface point, therefore it's not in shadow. But let's look at this surface point, right? So when this point is transformed into light space, and we basically determine, again, relative to the light source, how far away is that point? Then all we have to do is compare that value to the Z value stored in the light's shadow map. And this value is going to be a whole lot larger than this value, right? Basically telling us that this point right here is in shadow. It is farther away than the closest unobstructed point from the perspective of the light source. So that is the basic idea behind how shadow maps work. And actually, to show how shadow maps work a little bit, I'm actually going to use Blender here just because the Eevee rendering engine inside of Blender, it's a really fantastic real-time rendering engine. It gives us some nice tools to just really easily see how shadow mapping works, and also gives us a great way to work with some soft shadows, which are fantastic, and we'll look at those in just a second here. So yeah, inside of Blender here, I am just going to quickly I'll just create an area light, because we'll need that for the soft shadows in just a second here. But let's just position that area light and go into our rendered view here. I'll actually just increase the intensity of that light so that we can see what we're doing here. All right, so this shadow that you see here is being generated using a shadow map for the area light. Let's take a look at the settings here 4 shadow maps for the rendering engine. And this is where the idea of the resolution of the shadow map is going to come into play. Really interesting to see, like the idea of texture resolution or image resolution come into play with light sources. Again, it kind of bends your mind a little bit to realize that this shadow is being generated using an image, but this is going to hopefully help explain that a little bit more. So what I can do, actually, we're currently working with a 512 pixel square image. Let me drop the resolution of this shadow map down to a very low resolution, right? So only 64 by 64 pixels being used to store these Z values, right? This depth information from the point of view of the light source. And well, let's take a look at the results, right? We have a very pixelated shadow here. And of course, increasing that resolution is going to allow for more and more refined shadows. Now, important not to call this a soft shadow. This is not a deliberate softening of a shadow. It is simply low resolution and low quality shadow map. All right, we could maybe bump that up to maybe 1024 or even maybe a 2K shadow map to really make the edges of this perfectly hard shadow nice and crisp. All right. Now for performance here, maybe I'll just keep it at 1K. And let's talk a little bit about an approach for softening your shadow maps. All right, now there's multiple ways to approach this. However, we're going to see something kind of similar to the method I briefly mentioned with regard to projection shadows. And of course, that was this whole idea of simulating different point light sources, emitting light across the surface area of the light source. So what I'm going to do just to start off with here is I'm actually going to drop down my samples to 1. We'll see what this whole sampling idea does in just a second here. But let's go ahead and turn on soft shadows and then just increase my render sampling to a value of 2. Okay, so with 1 sample here, again, we're not going to get into the details of how the Eevee rendering engine works, but in the context of sampling a soft light source, 1 sample would just be simulating 1 point light source, basically somewhere on the surface of this area light. And well, we can see here just by aligning our view with the area light's point of view, we can see that that point light source is being simulated as right at the center of the surface area here. Now with 2 samples, take a look at the shadow that we are generating here. You can see there's like a copy of that shadow, a slightly different hard shadow being produced from a location, slightly not at the center of the area light, right? So as we increase the sampling here and get more and more light samples, we're basically simulating these shadow maps being produced from different points around the surface area of the light source. Let's drop this back down to 2 samples actually, and let's just quickly revisit something from the lecture on light sources. All right, so what if we wanted to harden up this soft shadow a little bit? Well, we know that small light sources with a physically small surface area, give fairly hard shadows, and we can see that happening here as I shrink down the scale of the area light. And in contrast to that, a large light source will give softer shadows. All right, we can see that very clearly here. A bit abstract with only 2 lighting samples, but just to show clearly what's happening with the different point light sources being simulated across the area of this area light, we can clearly see what's happening here. Now, of course, we would have to drastically increase the number of light samples being used here to get anything remotely convincing. So, even at 32 samples from a distance, that does start to look good. And, definitely with a bit of, or the magic that certain denoising algorithms bring into real-time rendering, certain artifacts like this can easily, certain artifacts like this weird banding can be done away with, or we could increase the number of light samples even more, right? So that just gives a quick idea about like how soft shadows could be approached in real time. Again, there are multiple ways of approaching this, and Eevee only really presents one of those options to us. All right, so there's shadow mapping, a fantastic real-time shadowing technique. Hopefully that was useful and fun to see it in action in some 3D software.